Welcome to our presentation on boosting monocular depth with panoptic segmentation maps. I am Faraz Saeedan, and this is joint work with Stefan Roth from TU Darmstadt. Monocular depth prediction is inherently ill-posed. This has been addressed by leveraging semantic representations in deep networks, yet supervised learning suffers from sparse and noisy depth data. Self-supervised learning offers an alternative, but training from image data alone limits the accuracy. In this work, we propose to augment self-supervised approaches with auxiliary information from panoptic segmentation maps. This is based on the observation that prominent boundaries in depth maps often coincide with edges in the panoptic maps. We base our approach on monodepth, a stereo-based self-supervised technique which relies on appearance matching for training the monocular depth prediction network. Previous work that explicitly leverages semantic information includes semantic monodepth and SceneNet. The semantic information augments appearance matching and leads to improved accuracy. In contrast, we leverage panoptic segmentation maps, which not only distinguish between different classes of objects, but also between the instances of the same class, highlighted in red in this example. This is important, as typical scenes exhibit partially overlapping objects of the same class, such as the cars here. Overlapping instances usually have depth edges in between, which cannot be identified from semantic maps. We propose to overcome this with panoptic segmentation maps. Our model is comprised of two elements, a geometric baseline shown here and the panoptic boost. At test time, our base network predicts disparity from a single image. During training, left and right disparities are predicted separately from each view, and then appearance-based matching loss is used for self-supervised training. We propose to apply a panoptic boost during training based on three novel panoptic loss terms. First, panoptic left-right consistency ensures the consistency of the left and right panoptic map. The benefit over appearance matching is that panoptic maps are not susceptible to photometric differences from the amount of light reflected. To avoid the need for an explicit panoptic map also for the right view, we instead warp the left panoptic map twice using the right and left disparities and check that the panoptic segment index did not change. Next is panoptic guided smoothing. Typical self-supervised approaches apply contrast-sensitive smoothing for regularization. This assumes that image and depth edges coincide. But images have many additional edges, such as from surface textures, which are erroneously propagated into the depth maps. Panoptic maps, in contrast, have no trace of surface textures. We thus perform edge-aware smoothing based on panoptic discontinuity, regularizing depth within but not across panoptic segments. Finally, we propose a panoptic-guided alignment term, based on the observation that panoptic boundaries indicating a change of class, instance, or both, are likely to also have a relatively strong edge in the depth map. We encourage depth edges at these locations. We first evaluate the case when panoptic ground truth annotations are available for training here on cityscapes. Our panoptic boost, when added on top of monodepth, shows clear improvements over other baselines that exploit information from semantic instead of panoptic segmentation maps. Note that we neither require nor predict panoptic maps at test time, hence our approach incurs no computational overhead. Looking at a qualitative example, we see that the purely self-supervised geometric baseline exhibits visible artifacts caused by transferring texture into the depth map. Leveraging semantic maps, in addition, avoids this. But since different instances are lumped together, their relative depth appears incorrect here of the marked pedestrians. Using our panoptic segmentation-based loss yields the best result. When panoptic ground truth data is not available at training time, our panoptic boost can still be applied. Here we evaluate on the eigensplit of Kitty, precompute the panoptic maps using an external panoptic segmentation network, and use the predictions for boosting the geometric baselines monodepth or monodepth 2. In both cases, leveraging panoptic maps results in a steady improvement of the depth prediction. In conclusion, we propose a method to boost self-supervised learning for monocular depth prediction with information from panoptic segmentation maps. We can leverage ground truth or inferred panoptic maps at training time. At test time, our approach incurs no overhead, can easily be added to various depth estimation networks, and provides a substantial boost in accuracy. Thank you for your attention.